Welcome to the Explainer. Today, we're going to get right down to the fundamentals. We're breaking down the science of energy. The force that powers absolutely everything, from the tiniest chemical reaction all the way up to our entire planet.
So what do your lunch, your car, and a skyscraper all have in common? Well, it might sound like the setup to a weird joke, but the answer is energy. Every single one of these things either provides it, uses it, or needed a massive amount of it just to exist. And where does pretty much all of that energy come from originally? Yep, the sun.
Okay, so here's our game plan to get our heads around this. We're going to start with the basics of what energy is, then look at its two main forms. After that, we'll untangle the often confused difference between heat and temperature, and finally, we'll see how all these big ideas are shaping the future of our world.
So, before we dive into the nitty-gritty definitions, let's just take a second to appreciate how completely essential energy is. I mean, the fuel in your food, the gasoline in your tank, the process that forged the steel in our bridges, it's all about changes in energy.
So what is it, really? Well, in the simplest terms, energy is the ability to supply heat or to do work. And doing work is just a fancy science way of saying it has the power to move stuff. Whether that's a car speeding up or a kettle boiling water for your morning coffee.
Now, energy comes in all sorts of flavors: chemical, electrical, thermal, you name it, but they all fall into two main categories: energy that's stored up and energy that's on the move. And pretty much everything around us is constantly flipping between these two states.
On one side, we have potential energy. Just think of this as stored-up power, energy that's waiting on deck to be used. And on the other side, we've got kinetic energy, which is the energy of motion. That's energy in action.
A perfect way to picture this is a hydroelectric dam. All that water held back in the reservoir, it has an immense amount of potential energy just because of its height. But the second you release that water, its potential energy converts into kinetic energy, spinning a turbine to generate the electricity that lights up a whole city.
And this brings us to one of the most fundamental rules of the entire universe, also known as the first law of thermodynamics. Basically, the total amount of energy is constant. You can't just create it from nothing, and you can't make it disappear. It just changes its costume, shifting from potential to kinetic, from chemical to electrical, and on and on.
So, this brings us to three words we use all the time, but let's be honest, we often get them mixed up: thermal energy, temperature, and heat. They're all connected to motion at the molecular level, but they are definitely not the same thing.
Let's break this down. Imagine you've got two pots of water. One is a tiny cup at 90 degrees, and the other is a giant bathtub at 30 degrees. The temperature of the cup is way higher. Its molecules are zipping around faster on average. But the bathtub has way more thermal energy because it just has vastly more molecules in total. And heat? Heat is just the energy that flows from that hot cup to the cool air around it. It's the transfer.
And this natural flow is something you see every single day. It's why your hot coffee eventually gets cold. It's literally giving its thermal energy to the cooler air. An ice cube melts for the exact same reason. The warmer air is transferring energy to it. This whole process keeps going until both things reach the same temperature. We call that state thermal equilibrium. Okay, so when chemical changes happen, they can either push heat out into the world around them, or they can pull heat in from their surroundings. This gives us two more really key ideas.
It really just comes down to the direction the heat is flowing. An exothermic process, like a campfire, releases heat into the world, right? It makes everything around it warmer. But an endothermic process, like what happens inside an instant cold pack, does the complete opposite. It sucks heat from its surroundings, which is why it feels so cold when you touch it.
All right, here's a classic for you. Have you ever wondered why on a cool day, a metal park bench feels so much colder than a wooden one, even when they're the exact same temperature? Or why it takes forever to boil a pot of water? Well, the answer is in a material's unique thermal personality. This property is called specific heat capacity. It's basically a measurement of how much energy a substance has to soak up before its temperature will actually go up. You can kind of think of it as a substance's thermal stubbornness, its resistance to changing temperature. So, if we take a look at a few common materials, their specific heat values can actually tell us a whole lot about how they act in the real world.
And yeah, the numbers do not lie. I mean, look at water. Its specific heat is incredibly high. It can absorb a massive amount of energy before its temperature even budges. This is exactly why coastal cities have milder climates than places inland. Metals, on the other hand, have really low specific heats. It takes hardly any energy to make them hot, which is why your metal seatbelt buckle can get unbelievably scorching in the summer sun.
And hey, this isn't just some abstract idea, we can actually calculate it. Now, don't let the letters scare you. This equation is actually pretty simple. It's how engineers figure out everything from how much energy it takes to boil water in a power plant to how to design a better coffee thermos. It just connects the amount of heat, Q, to a material's specific heat, C, its mass, M, and the change in its temperature, which we call delta T.
So, why does all of this actually matter? Well, because understanding these fundamental rules of heat and energy is absolutely critical if we want to develop the technologies that are going to power our world more sustainably.
Just look at large-scale solar thermal plants. They are a brilliant application of all these principles. You've got thousands of mirrors focusing sunlight onto one central tower, heating up a fluid inside. And the key here is choosing a fluid with a really high heat capacity, like molten salt, that can absorb and store a huge amount of that solar energy.
That stored heat is then used to boil water, create steam, spin turbines, and generate electricity, sometimes for hours even after the sun has gone down. The Ivanpah plant, for instance, produces enough energy this way to power over 140,000 homes.
So you see, it all comes back to that one fundamental law. We can't make energy. We can only change it from one form into another. By mastering these principles of heat, temperature, and specific heat, we can get a whole lot smarter about how we capture the sun's energy and transform it into the power that runs our modern world. The real challenge isn't creating energy. It's mastering its constant cosmic dance.